Hi guys. So I want to present you the NFT classifier literature review. So this is the third model that I'm currently developing. I'm working on that with one partner, Leonard, that couldn't join the call. A few words. First, image classification usually classify an image of a single object, assigning it a specific label. When we talk about object detection, it's usually detecting instances of objects of a certain class in an image, and it both includes classification and localization of multiple objects in an image. Object recognition is a combined task of object detection plus image classification that's performed by computer vision techniques. And we consider that NFT classification using computer vision is a perfect fit to explore the latest state-of-the-art in convolutional neural networks with feature detection. So this is in short, the literature review that we will present you. You have more on the GitHub, but there are three important articles that we wanted to share with you. The one that's comparing the performance of the models in art classification as an overview. You have the one that's called Mapping the NFT Revolution. It's using different market trends, trade networks, and visual features to predict the values of NFTs. And then you have the one called Compounding the Performance Improvements of Assembled Techniques in a CNN, where they are exploring how different improvements can significantly increase the image recognition. So let's go. The first one, Compare the Performance of the Models in Art Classification, has been published in 2021. Mostly, it's art classification done by artificial intelligence. And they are explaining that there are different trends like the increase of digital art and the digitalization of existing artwork from museums and other galleries. Are making it more and more available datasets online, and that combined with the fact that computers are learning genre, styles, and artists more and more easily because they are more and more powerful, so it allows us to create large-scale art classification models. So in that paper, the authors are using a protocol that's the following. So they are using three different data sets on 7 pre-trained CNN of the res family. And they are training the models by telling them which artist, genre, and style are the different paintings. So as you can see on the first illustration, on each stripe you have one artist work, like Vincent van Gogh, Maurice Prendergast, and Paul Cézanne. And each of these paintings are categorized depending on the style and the genre of painting. And then the testing task consists in classifying paintings by using the feature extracted and telling the user what kind of artist or genre or style is the painting presented. So the experimental setup for each model is consisting of transfer learning. So they are using pre-trained model on general images, AlexNet actually, are adapted by matching the last fully connected layer to the number of art classes, and random initialization is used in the last fully connected layer and the pre-trained ways in the other layers. In terms of training, the CNN learns artist, genre, and style on multiple labels separately, and he's extracting visual embeddings, then use it to classify paintings. In terms of evaluation, the model is choosing the max accuracy after k epoch of training, and the fine-tuning is done by a stochastic gradient descent with L2 regularization. The key takeaways of that article is that dataset with categories of a few images led to worst results, so it seems important to have a balanced dataset of equivalent collections of art. The style embeddings count a lot in the classification performance, maybe more than artist or genre, probably because, yeah, this is the most important in terms of influence for detecting which paintings is what. When TSNE algorithm is used for dimensional reduction, the models learns more visual embeds and improves results. Optimized model architecture improves the recognition rate, but the recognition distribution keeps the same, which means that actually models are improving their ability to detect the which paintings is newly presented to them, but they keep struggling in the styles or artists that are not well defined, because maybe they did different styles in their life, maybe because their style is overlapping with another kind of similar painting style. So yeah, what's good news is that real-world image classification are working on art classification. So it means like as much as we improve Street View images classification, for example, it will be useful for art as well. And we also detected that further training with similarity search engine are improving the classification. So that's another way for making better and better results. On the second paper, mapping the NFT revolution, different methods or inputs are used. Actually, what are NFTs? NFTs are non-fungible tokens. It means like they are digital data. Could be images, video, book, music, albums, but mostly nowadays NFTs are images, and the ownership is secured by a blockchain recording, making it a tradable financial asset. And because NFTs are uniquely identifiables, they can't get subdivided in smaller units like gold or any kind of currencies. As for overview, from 2017 to 2020, about $60,000 of daily trades were recorded for NFTs. And this exploded in early 2021, reaching the point of $1 million of daily trades for NFTs only. Most traded NFTs are collectibles and games. Art is less available but got the highest price on the market. And 1% of the traders hold 75% of market value, so it's very concentrated market. And as a result, traders have, let's say, less than 10 NFTs or more than 10,000. How does it work? Well, the authors have been using the pre-trained CNN AlexNet to analyze NFT images, which is extracted a vector of 4,096 values for each image, and giving this dense representation of images' visual features. The visual difference are calculated by causing distance within the same collection and between different collections, where 1 means that the two images are highly different and 0 means that they are identical. As a result, most collections are showing a great clustering between NFTs, but they are also heterogeneous collections that can exist. And a principal component analysis uses linear combination to lower the dimension to 5, because the original analysis was treating a lot of dimensions, and actually there is a lot of redundancy that can be just simplified using PCA. The key takeaways of that article is that 10% of traders perform 85% of all NFT transactions. They typically specialize on NFT associated with similar objects, and they have tight relationships with other traders exchanging the same kind of objects. So again, it's a very concentrated market. The collections contain visual homogeneities, and but also pictures from different collections can have similarities as well, since artists and creators are following the same trends. So as a result of all of this, we can say that visual feature increase predictability of historical sales analysis, probably because we know that most NFT traders are looking the same kind of object feature in images, and they also hold the maximum part of the market, the major size of the market. So visual feature is helping sales prediction and value prediction of NFTs. The last paper is called Compounding the Performance Improvement for Assembled Techniques in CNN. It has been published in 2020. And actually in this paper, the authors are using different improvement techniques for CNN and combining it to improve the image classification tasks. So since AlexNet, which is the mostly used pre-trained model in art classification, most studies has focused on new architecture design, like Inception, ResNet, DenseNet, NASNet, EfficientNet, but the authors are taking another lead. They consider that other aspects of network training can be combined to boost model performance, and in case they have been using data pre-processing, learning rate decay, and parameter initialization to have improved results, like state-of-the-art level results. So furthermore, the authors have been performing some network tweaks. They applied to ResNet model different let's say tweaks to reduce computational cost and increase accuracy. And they combined those network tweaks with regularization technique. Two of it, actually, data augmentation to prevent overfitting and dropout to limit complexity of CNN. So going fast to the different tricks they have been using. So the ResNet D change strides and convolution of the network. The channel attention is consisting of global pooling and fusing branches with softmax. Anti-alias downsampling is evaluating max operator and naive subsampling. And big little nets adjust widths and depths of the neural network. All these to reduce computational cost and increase accuracy. In terms of regularization, they used auto-augment as a reinforcement model to data augmentation, label smoothing, which suppress the infinite output bias, mix-up shows interpolated data to a neural network to avoid overfitting, drop block drops neurons on specific region of activation. It's a cool way to tailor the model dropout, the neuron dropouts actually. And knowledge distillation is consisting of transferring knowledge from complex models to lighter ones. The experiment results are showing that, ablation study for assembling network tweaks are having great evaluation metrics, and transfer learning improvements is being better for each model as well when using a combination of assemble ResNet FGVC50. The evaluation metrics that has been used are top 1 classification accuracy, throughput, number of images processed, MCE and MFR for mean corruption error and mean flip rate. As we can see on the first illustration at the left, the baseline model has been augmented with different network tweaks, and actually, they don't show all the same performance. We can see that the more there are added tweaks, the more the model is performing a good classification accuracy, and the less it needs a high number of images to process as an input. We can also add that assembling regularization technique increase accuracy, MCE and MFR. And for transfer learning analysis, well, as we can see, using complex model and transferring the knowledge to simple one is also showing similar accuracy for image classification, but increasing by up to 20 times the inference throughput. So very great results. The key takeaways of that article is that fine-grained classification and image retrieval tested on several public datasets, improving backbone network, improved the transfer learning, and existing CNN-related techniques can be assembled in a single CNN. So all this is very positive for those who don't want to, let's say, build complex network architecture. You can actually use the existing tools to combine them casually in an existing model and just improve that previously developed model to achieve the state-of-the-art performance. A few words about the project. So we tend to achieve NFT classification using computer vision, and it makes sense because most NFT are images which could match with buyer's feeling, mood, personal history, or even provide a self-fulfilling experience. I'm assuming people don't buy NFTs only like for speculation on values. So we consider that similarity search engine, which could be allowed by a powerful NFT classification model, would allow smart recommendation based on an NFT buyer's taste, and this could significantly help growing the NFT market sales. Thank you guys, hope you liked it, keep following.